So now we're going to find out how to find values of definite integrals. First of all, there's a lot of properties that go with them. We're not going to go over these individually, but we're going to actually use them through example. So these examples should help your understanding of the properties. So we're going to look at this graph of f of x, which is a funny looking graph. So it is a piecewise function. Consists of 4 linear graphs. That's what the equation is. You don't really have to worry about that because we're going to be just using the graph because it's going to be easiest in terms of definite integrals. So I'm going to show you the 5 basic types of situations you're going to see for integrals. The one key thing is, and these again are definite integrals, you can see the numbers right here. They do calculate area, and I say that lightly because they don't all calculate actual areas, but you'll be able to determine what the value is based off the areas. So with that being said, here we go. The first one is the normal integral. The lower limit is 0, which is on the left. Upper limit is 1, which is on the right. So basically, you're going to look at this graph from 0 to 1 and calculate the area. That's what a definite integral does. So if you look at this graph, we're going from x equals 0, that would be right here, to x equals 1. Now, when I talk about area, it's the area below the graph to the x-axis. So it would be this area. That's what the value of this definite integral would be. And this is a triangle. So this is 1/2 base times height. So it's 1/2, 1/2, base is 1, height is 1. So the integral is equal to 1/2. That's it. That's easy and should be. It's the normal integral. So the next one I want to take a look at is the integral of a negative function. So the one we just did was a positive function, and because the graph is above the x-axis, that's positive. If you look at B, we're going to do the integral of a negative function because if you look at the limits, we're going from x equals 3 to x equals 4, which is from here to here. And if you notice, the graph is below the x-axis, which means it's negative. So here's how you handle that. This is an example where the definite integral isn't really going to calculate the area because when you calculate this integral and you still look at the area, but if the graph is below the x-axis, the definite integral is going to be negative. So you still are looking at the area of this triangle, which is 1/2 base times height, but if it's below the x-axis, which it is, the definite integral will calculate that to be negative, so this definite integral will be negative 1/2. So that's what I mean by a definite integral doesn't always calculate an area because negative 1/2 is not an area. The area of this region is 1/2, but the definite integral would be negative 1/2 because it fell below the x-axis. The next question is a combination integral, meaning the graph is going to be both above and below the x-axis between these two limits. So we're going from -2 to 0 here. So we start at -2, we end at 0. So the first part of the integral, the -2 to -1 part, that area will be calculated as negative 1/2 because it's below the x-axis. And then it flips to above the x-axis. So you have to do this in two separate calculations, plus this area, which is a positive 1/2. So this is 0. So a definite integral definitely can be calculated to be 0. Now it's very obvious it's not calculated in area, because if you look at this total area, it would be 1/2 plus 1/2 is 1. But the definite integral calculates it as 0. So just again, a definite integral does calculate area only if the graph is completely above the x-axis. Otherwise, it just calculates a number. So the next type of integral is a backwards integral. What I mean by that is all of these integrals have been calculating left to right here. If you look at this integral, the 2 is on the bottom, the 1 is on the top. So it's doing the integral from 2 to 1, which means it's going from right to left. So to handle that, you're going from 2 to 1. The only thing that changes is when you go backwards, the number that the integral calculates will be opposite of what it would usually calculate. In other words, if we went from 1 to 2, it would be a normal integral, and the area, the definite integral would be 1/2. But since we're going from 2 to 1, it's going to calculate that as an opposite number. In other words, negative. So negative 1/2. So if you think about it, a normal integral, if the graph is above the x-axis, it always calculates positive. If you go the opposite direction, though, it will calculate as a negative. So same thing as if I were going to calculate the integral from 4 to 3. Usually that's negative, but this integral would calculate as positive. As a matter of fact, if you ever want to switch the limits of an integral, you may find a reason to do that from time to time. You could say this integral, if you don't like going from higher number to a lower number, you can always write it as negative and then lower number to higher number and just do this part of it as usual. So the last example is a backwards combo integral, meaning I'm going to go backwards and I'm going to go through both negative and positive graphs. So we're going to calculate the integral from 4 to 1, which means we're starting here, we're going this way, and we're ending here. So the integral is going to calculate this area, but it's going to calculate as positive because we're going backwards. Usually it would be negative, plus this area, still going from right to left. Usually that would be a positive 1/2, but we're going backwards, so that's negative 1/2. And then finally, it would calculate this area. This is still normally positive, but we're going backwards, so that's still negative 1/2 again. So it's a negative 1/2 minus 1/2 minus 1/2. This integral is negative 1/2. Hopefully that made sense. Those are the only situations you're ever going to encounter. So the rest of the stuff should be pretty easy. We'll do a couple more examples on the next video. So we'll see you then.